Here we're going to talk about using implicit differentiation to analyze a function a little bit. Let me really quickly do this derivative. We got 6x squared minus 6y dy dx equals 0. So 6x squared equals 6y dy dx. So dy dx, if I divide, is equal to x squared divided by y. Okay. Now, I'm going to go back and find the second derivative in a few minutes, but let me just start by kind of doing some analysis with this. Find where the slope is 0. Well, the slope, of course, means derivative. Okay, this means the derivative is 0. dy dx. So, to figure out where the derivative is 0, we just look for what would make the numerator 0, because of course 0 divided by anything is 0. So the slope is 0 when x is 0. Okay, so that's kind of our, let me put a little dot there, that's kind of what we're going to check, that x is 0. Okay. Now, let me go back to the original function. Okay, original function. And let me assume that x is 0. Let me plug in 0. So I get 0 minus 3y squared equals 8. So negative 3y squared equals 8. So y squared is equal to negative 8/3. Well, the problem here, of course, is we can't take the square root of a negative without getting into imaginary numbers. So it doesn't work. So this is kind of tricky in that what we said was x had to be 0, but when we plugged 0 in, it doesn't work, meaning there is no place where the slope is 0. Now, this has not happened in explicit functions. Implicit, we have to check to make sure the derivative and the original function agree. We didn't do anything wrong. According to the derivative, if x is 0, the derivative is 0. That's correct. But what we find out is that when we plug 0 in, we get a non-real answer. So there's no place where x is equal to 0. This has been on the AP exam before, and basically in this way, where it says, show that there's no place the slope is 0. And the method was just like this, where it said, well, or the answer, for the slope to be 0, x has to be 0, but x can't be 0 in the original function, or we end up with a non-real answer. Okay. Now I'm going to drag the graph in here in a minute and show you that, but let's just do the slope is undefined here as well. The slope is undefined, of course, means the derivative is undefined, so for that we look for where the denominator is 0, and in this case, of course, that's where y is equal to 0. But we got kind of, heard on this before, so we should plug y into the original and see what we get. So 2x cubed minus 0 equals 8. So of course we could ignore that. So x cubed is equal to 4. So x is the cube root of 4. Okay, now let me grab this graph real quick and pull this in. Here it is. It's kind of small. Okay. A little bit bigger. What you see is kind of a weird half hyperbola, but you see that when y is 0, we do have a vertical tangent right here. When y is 0 and x is the cube root of 4. But this just goes on forever and ever in both directions. So there will never be a place where the slope is 0. There is a spot where it's undefined. We have a vertical tangent, but we don't have a horizontal tangent. Okay? Okay, let me go back and find the second derivative now. We'd notate that like this. The second derivative, of course, was just the derivative of the derivative, so we need to use quotient rule. Low d high minus high d low, cross the line and square the low. Well, what makes this tricky to look at is we have three variables because we've got this dy dx. But the nice thing is I know what dy dx is equal to. So I could do some substitution. I could say, 2xy minus x squared multiplied by x squared over y all over y. And you could keep going at this point. You could say it's 2xy minus x to the fourth over y. Oh, sorry, it's y squared here. Maybe then multiply by 1 over y squared. You could get some cancellations to work out. There's a lot you could do. I'm just going to put this. There's a lot of simplifying that could be done. But essentially, we do the rule and then substitute dy dx in. One more time, let me do one more derivative here. So derivative of 2y is 2 dy dx. Derivative of x squared is 2x. And derivative of sine y is cosine y dy dx. So we get the dy dx stuff on the same side. Factor the dy dx out. Divide. Here's my derivative. If I want the slope to be 0, I need to set the numerator equal to 0. Okay, I'm just going to write the numerator of the derivative. Of the derivative has to be 0. So if 2x is equal to 0, of course that means that x is 0. Okay. Let me put slope as 0. Let me put an arrow here. We'll do all this work in black. Well, we got burned last time, so where we said the derivative has to be this and it didn't work out. So let's plug in 0 for x and see what we get. 2y equals 0 squared plus sine y. So it's just 2y equals sine y. Well, that's kind of a hard one to guess. You could certainly do it graphically, but the sine of 0 is 0, and 2 times 0 is 0, so y would be 0. So what we just find out is there is a coordinate, x is 0 and y is 0, where there's a horizontal tangent. Okay, I'll show you the graph, but there is a spot this time that works. Slope is undefined, of course, means the denominator of my derivative is 0. We do this work in red. So that means that 2 minus the cosine of y is 0. So that means 2 is equal to the cosine of y. Unfortunately, from your work with cosine, you know that cosine has a maximum value of 1. So that doesn't work. There is no place where cosine is 2, so there is no spot where the slope would be undefined. Now let me pull a graph in here so we can kind of verify that. Make it a little bit bigger if I can. Okay, here's what we see. The spot 0, 0, the origin, we have a horizontal tangent, but it kind of looks parabolic, of course adjusted by the trig function, but it looks kind of parabolic, and that's why there is no vertical tangent or undefined slope.